Since unfortunately the speaker could not be here with us, we are skipping now the Q&A session and will directly move over to the next talk, who will be presented by François Pomerleau, who is a professor in the Computer Science and Software Engineering Department at Laval University and heads the Northern Robotics Laboratory, or so-called NORLab. His research in SLAM mapping and robots operating in harsh conditions is widely recognized and received several best paper awards. His research is specialized in mobile and autonomous systems working in northern or difficult conditions, pushing the boundaries of what is currently possible with a mobile robot in real-life conditions. His lab currently focuses on localization algorithm designs for laser sensors and 3D reconstruction of the environment. As you may have noticed, François could also not be with us because shortly before the flight, he could not go because I think his wife contracted COVID, and therefore, it's the same unfortunate reason as Denwei in the beginning. But while François could not be with us, we were lucky that we have Philippe, who's the co-director of the NORLab, who offered us to answer some questions on the talk. So while we had no Q&A for the first talk, we will have some Q&A and some opportunity to ask Philippe about his work after the talk. So enjoy the video.
Hello everyone, I'm sorry to not be with you today. I guess I had what you all figured at some point, which was Credit was invited at home 2 days before I left for the conference. So we decided that I should record the video because I will be sleeping while the workshop is ongoing. So let's start. Today I will talk about from Subarctic to Subterranean, how to localize in unstructured environment. That will cover what we do as a research lab in Quebec City recently. So in September 2021, we concluded our participation to the DARPA Subterranean Challenge, in which we won 9 awards and could raise up to $3.3 million in both cash prize and research funding. And meanwhile, the same thing was actually doing our first 20 kilometers of autonomous driving in the Subarctic forest. But before we go into the details, a quick word on me. So I'm doing mostly research on SLAM and field robotics since 15 years. I started at ETH Zurich for my PhD. Since then, I did multiple field deployment in Europe, United States, and Canada, from the Swiss Alps here for autonomous bulk sampling up to underground mining, which is the case for the Subterranean Challenge. We collaborate with first responders, the industry defense, the government, and special agents. Since then, I'm the founding director of the Northern Robotics Laboratory, NORLab in short, and we are located in Quebec City, Canada, and we are piloting 3 major research trusts. The first one is research project SNOW, that we will talk about. We have another branch called AI for forestry activities, and we just concluded our DARPA Subterranean Challenge participation. So the content of today would be DARPA, then key results of SNOW, and future directions where the lab is heading. So let's start with the DARPA Subterranean Challenge. Maybe you know or you don't, but it started with there was multiple level, let's say, or environment for the competition. The first one was tunnel or mine in 2019, and then we move on to more urban area in 2020. Everybody was expecting an underground metro station, but we were actually in the decommissioned nuclear plant, which was quite spooky, but quite interesting. In 2020, there was supposed to be another challenge in natural cave, but that one was cancelled due to COVID. And in 2021 was the final, which was combining mine, natural caves, and underground environment. I think people don't talk a lot in their talk about the ranking, but here it is. You have the numbers, which is the number of points that were scored for the system track for each of the environments. And we could see that we were doing pretty well until there was some mixes with COVID. And maybe one of the conclusions of that, so here's the final teams. Cerberus finished first, and Cyro second, and Marble third. And what is interesting here is it was rather stable at the beginning. And I think that's an hypothesis that all the teams down here was handling multiple universities and even multiple country collaboration. And with the pandemic hitting, that was costing us a lot. And in our case, actually, we're not able to integrate anymore. Nonetheless, there was also a virtual track, which was not that much popular at the beginning. So again, that's the ranking, the number of points that each teams received. And when the pandemic started, there was way more teams first, and also a couple of teams that crossed from system to virtual. And that's our case, and this is where actually we perform at the end at the second place. Just to give an overview of the final. So here's the map that DARPA was providing to us. That's their grant route. And in purple and green, we see some test run that we did after the competition. So just to give you an idea, there was everything was staged, except this one, which was the natural place. And that one, so we were in the Mega Cavern in Louisville, Kentucky. Here's the starting position where all the robots would start. And you have key examples of the different area. So here was more the natural cave. In that section, here was the old school mine, then more modern mine in that area. And in green, it's covering mostly underground urban environment where DARPA built essentially a underground subway station from scratch only for the competition with fake paintings and sign and everything. So they went crazy with the decor and the station. One key paper, if you want to know more, that I would like to direct your attention towards, we have a SLAM survey paper, which is currently under review and transaction in robotics, but the preprint is available. So it's called Present and Future of SLAM in Extreme Underground Environments. What is interesting about that paper is that first it gathered all the top 16s, and in one paper you have all of the SLAM architectures that were used. So it's a bit easier to understand what is happening. One of the key takeaways that I have is that actually all of the teams use a LiDAR IMU-based solutions for underground exploration. And also you will find some dirty details, even the link to all the public repo that were used for the competition and key point to orient your future directions. So definitely you should have a look if you want to just know what happened during DARPA Subterranean Challenge. So talking about SLAM solutions, our was only LiDAR-based audiometry, help with an IMU, of course. So here's our map buildings algorithm on the way. That's again during the test run after. During the competition, we didn't move that far because of communication and exploration algorithm issue. Here you can see that it's actually quite stable. We have a drift of less than 1%. And because we're doing also other experimenting on very large scales, so more in the kilometer range, we have tools to tile the 3D map and keep the memory. So here, for example, that part is here, to keep the memory under control for real-time application. A bit more detail on our pipeline. This was actually published during IROS, so the talk happened 2 days ago, but the preprint is available also online. It's something that we call priority constraint point cloud registration. So essentially, it's a relatively simple trick, which is using the gravity vector as a global Q. So we, instead of minimizing the 6 degree of freedom, we minimize within the ICP iteration only 4 degree of freedom, and we fix 2 of the orientation using the gravity vector. So here are some key results that were evaluated on the dataset, which is, by the way, publicly available. So if you want to access those point cloud, they are offered by DARPA. We have the 2 evaluation graphs. The first one is the z-axis errors in meter. The second one is the absolute translation error, also in meter. So we see that on the absolute translation error, the gain is not that much, but when we only look at the z, so the error in elevation, we are able to smooth and reduce by quite a lot the error. So in the paper, we evaluate that we can reduce by 30% the drift in LiDAR telemetry with that. Just to give you some context, so here's the farthest point, which is 190 meters from the start, roughly, depending of the path, and that peak here is over here. We have also the same evaluation. So again, the gain on the ATE is not that much, but when we only look at the zero, which was one of the axes that we were trying to limit drift, we can see that using the gravity vector helped a lot. This pipeline was also evaluated off-road in the Subarctic forest. So that's the full map. Now we're talking about the 1.5 kilometer. So this is where the tiling gets useful, because we need to provide real-time localization to that robot during our experiment. So during that one, we could limit the drift of 55 meters over the course of 1.5 meters. That simple trick of using the gravity vector. So this makes a good connection with the second part of the talk, which is our SNOW program. SNOW stands for Self-Driving Navigation Optimized for Winter. It's a project in collaboration with General Dynamics and System in Canada. It's a 5-year research project that we are about to close, and we'll ask for a renewal for the next 5 years, working in the same kind of topic. So working in snow and ice, recently we developed quite some expertise. This is where I start to build up a new word, which is cryorobotics. Cryo for the mix of cryosphere. And here we see the different place of the cryosphere. The definition of cryosphere is essentially where you can find water at the solid state. If you're interested in starting research in that area, I invite you to have a look in the paper Robotics in Snow and Ice for the Encyclopedia of Robotics. The preprint is also available, but for that talk, we'll focus on frozen ground and deep snow cover. So where we're doing our test, it could be up to 1.5 meters of snow in which we need to navigate. So again, we are in Quebec City. This is the area, the part of the world. And to give you an idea of the scale, we at Laval University, we have access to a research forest. which is quite large and had the advantage of being remote, and there's snow there 6 months per year. So even though it's relatively short distance from the city, so maybe an hour of driving, and we have all the facilities to stay for typically a week up there. We extend the snow seasons by 2 months essentially, and there was way more snow up there. So one of the key results that we had is, like I said at the beginning, our 20-kilometer of autonomous driving, where we did teach and repeat and back and forth during night, days. It was snowing. We actually had quite some good snowstorm. So here's the difference between the different locations. So within 1 week, we could cross at least 4 different kinds of weather. The snow was melting, then it was snowing, then it was raining. All to show the complexity of navigating in such environment. And since it's the theme of that workshop, I just wanted to highlight what we consider as unstructured and dynamics. And please, so have a look at or focus on the trees. For example, here it was actually snowing, but we were at the end of the snowstorm. The drone had some difficulties to stay on position, and we could see that actually, although trees look like good stable points, they can bend and move quite a lot during a windy day. Again, here's our localization pipeline. It's exactly the sign that we use for DARPA, as you could see in the video, moving through a narrow path in the wood, hopefully look like navigating in a tunnel. So we could liberate from both research. This concluded in a paper for the field robotics, the journal Field Robotics, called Kilometer Scale Autonomous Navigation in Subarctic Forests, Challenges and Lessons Learned, in which we make a point of differentiating between what is a forestry road, which are usually quite large, and a trail, and we focus the evaluation of the trail. So we use the teach and repeat framework to actually highlight some key elements about the weather, GPS, GNSS, navigation, and LiDAR. So for example, here's all the different kind of weather we cross. In blue, you will be the snowstorm, in purple, mostly rain, and actually you can see the difference in temperature that we crossed within exactly the same week. So it was a continuous week where we crossed all of those weather conditions. For the GPS, the trail is quite narrow, and the GPS signal get occluded at some point. So we could see that with the number of satellites observed at some point, even GPS navigation would fail and will get out of the deviate enough that would collide with trees and so on. So in our evaluation, that happened with less than 18 satellites in deep. We also did a deep analysis of LiDAR-based odometry, the same as we use for DARPA, and highlight the problem of corridor in wood, essentially. So those were key results of our group. Now where we are going with that, we just got approved for another 5 years research project called WAVE, so for waveform analysis for vehicle in extreme scenarios, in which we partner with LiDAR Tech, which is a LiDAR manufacturer. And we ask ourselves, now that we know we can navigate with radar, which is mostly 2D with large beams, we are more and more used to the 3D maps of LiDAR, which is very fine and crisp. But is there something in between where we could actually see through snow and a bit around obstacles to help navigation in off-road and winter conditions. And we are working also very hard to partner with NASA GPL on the exobiology existing life surveyor, which is called EELS in short. The general goal of that project is to have a robot exploring a moon of Saturn. And of course, now we're talking about ice, which get under our expertise. This is the long-term vision, but short-term, the idea is to explore those moulins. So when water is melting, it's going down those holes, and we want to test our localization pipeline in those environments. Finally, like I say, we are renewing with General Dynamics and Hydro-Quebec, which is the larger hydropower manufacturer based in North America. Where we want to continue our off-road navigation. There's a lot of stations that need to be inspected in north of Quebec, at least. And something that is interesting here is that we are talking about critical infrastructure. So if a problem happens, we can cut the power of 2 million inhabitants by shutting down one of those stations. Or here, and we see how they do it. Currently, inspection for the power line, which implies essentially having an helicopter and snowmobile that are shipped around. So that's the conclusion of the end of my talk. If you have any questions, don't hesitate to write me directly. We are present on many social media, and we have cool YouTube videos where we essentially throw robots into the lake and try many random things, not just science stuff. I hope you have a nice workshop. Stay safe.
So thank you, François. So if you have any questions, I'll try to answer them to the best of my knowledge, as I worked with François closely on many of those projects.
Okay, then.
Okay, so thank you very much. I'm wondering about localization accuracy in snow. So do you have some range?
So the one of the conclusions they had from the research is that actually falling of the snow is not so bad in terms of localization performance. It's more related to the long-term localization. What happened is you build your map on a Friday, let's say, and just to give you a perspective, like at the forest where we do the testing, the amount of snow that falls on over a year is basically the height of this room plus 2 meters. So what happened is it's going to change the map in a way that is not usual for, let's say, autonomous driving, which is basically the floor is going to go up. So the obstacles, like the obstacles are sinking. So what they see is it might create difficulties in localization because your maps become inaccurate unless you take into account the fact that the ground is going up. Because most map maintenance systems are about removing things, obstacles, like you took down a car has moved, or you're doing some repair on the road, but you don't have these cases where the ground is actually moving up. So that's one of the difficulties they find. But yeah, the actual snow falling is not too bad, unless it starts obstructing your sensors, which again is a different problem. Just like if you have optics, if you have scratches or particles on your lens, then it's going to might create problems. But LiDAR is surprisingly resilient to a snow condition.
So do you use a snow map or just only map collected in very nice weather conditions?
For the experiments they did, they collected maps during the winter, then they did a repeat part over several days, including significant amounts of snowfall. But they also tested like a few months later to see if they were able to localize, and they were indeed able to localize. But one can imagine that you can start building this kind of prior into your localization algorithm, which is to kind of neglect either the Z component or basically not take into account too much the height of the ground, because it might change significantly.
And the final one, so what kind of localization method have you used?
It's mostly LiDAR based, like iterative closest point, where you have an a priori map built using LiDAR odometry. They don't use GraphSlam, but and the idea is As long as your navigation strategy is you make the loops short enough, then you won't have too much of a drift when you close the loop. And then you just relocalize within that map.
Yeah, so point cloud registration.
Point cloud, yes. There's no, at the
Just
moment, there's no vision based.
Oh,
And it's, yeah, you have to kind of give a rough estimate where you start in your map, maybe using GPS, and then
Yeah.
you will relocalize,
Yeah.
and then you'll start going. They did see some failures of reinitialization at the beginning, partially in regions in the environment where it was wide open and they had significant amount of snow, and also the snow doesn't fall like uniform because of the way the wind interact with the snow. It tends to kind of build these mounts. And also I think there was a car that was parked, that was not parked initially there. So they had a few cases where initialization failed, but once they were able to initialize the beginning of the repeat phase of the teach and repeat, then they noticed almost no failures.
okay, thank you.
Thank you for your question.
What kind of special features need a robot have to be able to navigate in the snow, like in the sensors or maybe in the wheels?
It's a good question. It's a hardware question. So there's the first thing is you have to get the right parts, like electronics. Like when we buy either cameras or computer equipments for the robot, we have to check for the temperature requirements, because some of the experiments are done at -17, -18, and most commercial parts stop at 0. So we have to make sure that we buy parts that are compatible till -20, which is a feat in itself. So of course, if the robot is warm, you start it, you operate it in the winter, it's not so bad. But the thing is, as the cold start, let's say you have a problem like the battery depletes, the robot's froze to -17, and you want to restart it, then it might be problematic, because things like cameras, which are in an enclosure, as long as they run, they generate their own heat. But once the system goes to a cold start, it's problematic, and it's a bit expensive on that aspect. So that will be the electronics. Now, in terms of the mechanical design, the best is to use tracks. That's why for the Warthog, we have this system where you have either wheels or these triangular tracks. And this is not Formula One performance. It takes about a few hours to change from one to the other. But even with the tracks, the thing is, the area that the tracks occupy on the ground is not enough for very deep snow, because very fluffy snow, like the system is going to sink maybe, or would like to sink by about 0.5 meter. So what's going to happen is the wheel maybe have a clearance about this much. So at one point, the trucks will start eating the snow or sinking, and then the belly of the robot, which is kind of flat, will rest on the snow, and then you can't move forward. So it's one of the difficulties. That's why, if you have a snowmobile, the snowmobile is basically you're sitting on a long track. That's what you do, because every point can be pushed forward. So if you would like to have an all-terrain, all-weather robots in the winter, I'd say you have to go through like a snowmobile. Thankfully, we know how to make these for about 60 years now. So it would cover the traction system. Also the sealing, just like, because you're operating outside, you have to have everything more or less sealed for the snow and the water. I'd say that's maybe the biggest components in terms of the design of the system.
Okay, very interesting. Thank you.
Thank you very much.
Yeah, you mentioned that the falling snow is not so much an issue for the LiDAR. So I'm wondering what the motivation behind using the waveform recorder would be.
I would say first is a cost thing. Like these solid state LiDARs, they're a fraction of the mechanical LiDAR. So the manufacturers, the car manufacturers are looking into this device because the mean time between failures is much higher than a mechanical device. So they're looking at maybe $100 or less than $100 manufacturing cost for these parts. And the idea is, like, the company right now, LiDAR, when you purchase their product, they're gonna give you like the first or second echo. So they don't give you a full waveform. But as research scientists, we're like, what can we do if we have access to the full waveform? Because we have access to a full waveform if you have access to the I don't want to call it the secret API. The problem is, if you have a full waveform, is the amount of data you're getting from your sensor is just ginormous. And also there's a lot of post-processing that is done on the chip itself that, we might be able to extract, I don't know, more information, from these full waveform, I would say.
Okay, so there's no specific target that you're looking for, though. Like target question to answer with the waveform. It's more.
Well, I think it's like because with the full waveform, you're getting more of a volumetric sense. Like a LiDAR, you can probe the surface, but now with the full waveform is like when François mentions about looking around obstacles, is if you have an obstacle which is relatively small, what's going to happen is you're going to have a first echo here, and then it's going to wrap around, and then you're going to find a second and third one. Well, the amount of light you get from the first echo will be much smaller than the next one. So you kind of get, like I said, a volumetric information. But you know, we just got the grant approved like literally 2 weeks ago, so we were very excited about it.
Yeah, thank you.
Yeah. So I have actually two questions. One is, are you trying to also traverse frozen lakes, and how do you estimate the thickness? If so, how do you estimate the thickness of the ice to be safe, to make sure it's safe? And the other question is, do you compare your mission, your overall mission completion against professional military troops like chasseurs alpins, alpine hunters? And you say it in English.
I guess it would be like maybe like mountaineers or mountain rangers. For the first questions, we've thrown the robot in the lake. It floats. So there's bilge pumps to remove the water from the. You know, if you notice the design, the two sides are like floaters essentially. So you could technically go across a frozen lake, and if you sink, it won't be too bad. But what you see, I'll speak from experience. Like I've seen many people riding snowmobiles over lakes and rivers, and it's a very dangerous thing. Every year we lose tourists that don't know what they're doing. They go and drive because it looks nice. You can go very fast. But one of the things they tell them is you go very fast, because if it starts sinking, then you have a chance of going over, because you're kind of be riding over the crushed ice that's going to fall down. So it's and also you have to have an understanding of the geography. Like, you know, that certain area of the rivers, the water will be stirring up a little bit more, or a lake near an entrance, so that you will have a prior knowledge that some areas are going to be thinner for the ice, and you will try to steer away from these areas. But no, we haven't tried to do it on a frozen lake, probably for safety reasons. It's extremely dangerous. I don't think the granting agency would love that, to say that, you know, they won't love that we lost 5 students this year. We need more money to replenish our students' funds. And to measure it, you know, right now what they do is they drill holes to know if it's thick enough to go on a lake. But I guess you can use a penetrating radar to go to measure it. And no, we haven't compared against humans. It's like the professionally trained people who can do missions. But I think in some sense, like some of the funding is from the GD, General Dynamics Land Systems. And I think they're looking at solutions like that for resupply between points, where I would say the cognitive load of a mission is relatively low, but the risk is very high, because in military, it's all about logistics, and it's usually your weakest point. And by having autonomous systems that can carry equipment between points, then I think even though they might have some failures, they're not catastrophic failures. Worst case, somebody will go and pick up the equipment. That being said, also for civilian applications, you know, the number of trucks that drive from A to B, like in mining industries, it's or even like forestry industry, it's always about driving between A and B. So,
thank you.
Okay, thank you.
Thank you. Do you have a plan to release a data set covering the snowy or underground environments?
I know we have released the data sets for the forestry stuff in the teach and repeat. If you go on our website, you'll find it. And I believe the data sets for the DARPA Grand Challenge are available through DARPA website.
Thank you.
Any other questions, comments? It's now your chance to ask something about snow, ice.
Yes, come and visit us. We have lots of snow.
It's very interesting. So I also was wondering for the initial question, so how do you get the robots operating in these conditions? And then, as you said, you really have to look for parts that are made for such conditions. That's
it is. I mean, you know, we have to go towards the mill spec or industrial specs, not the commercial specs, because there's a chance that the system won't start, and then because doing these trials are fairly expensive, because you have to rent a place for a week. So you don't want to be stuck at -17 with a frozen robot, and then everybody cries.
Okay, there's another one.
Just I am wondering about also for map generation using GraphSlam. So do you have some differences between generating map in snow or in normal weather conditions? So have you observed some difficulties comparing to?
I think the biggest difficulty is it's over multi-session mapping, where if you have snow between your mapping sessions, that's where you have this issue of the ground going up. I don't think they used any large tweaks between the if it's going to be like during the summer or the winter. The pipeline is fairly sturdy. I mean, it works on the ground, it works in the snow, it works in the regular weather. I'm sure there's a couple of parameters you have to tweak.
Yeah.
And also, the thing is, the environment is a bit more dynamic in the winter. Like you see, like the trees have these clumps of snow, and then if it winds, then the clumps go down or the trees are shaking. So forests are a bit tricky for that, because they're not entirely dynamic, but they kind of move a little bit over time. And also all they're devoid of flat surfaces.
Yeah.
Which often, if you do point to plane, makes it a bit more difficult. And also you have this fuzziness in your point clouds because the LiDAR beam goes through the branches, and that create kind of like a fuzzy, non-flat surface as opposed to perfectly flat surfaces of the cities. So it's definitely one of the challenges.
Thank you.
So if there are no other questions, I would thank you again that you offered your answering a very interesting question. I think we could also, in the coffee break that's coming now, you can further ask question about the harsh conditions and how it's to be in Canada, where I learned that you have even some things in the jacket that says like until when, which degrees of temperature the jackets and whatever are.
Oh yeah, I mean, you have to have good equipment. But as many people say, there's no bad weather, there's only bad clothes. So
okay, then thanks again, and see you.